thanks for the invitation, Matt. And I'm, happy to try to show you what we can do here as a few examples using computational approach or AI approach for mental health. And that's my group. What we are doing basically is we look at the data using human and mouse data, for example, look at mental health. And then we also working on modeling and theoretical side for artificial intelligence. But today I will concentrate on this part, using AI, what we can do using AI for mental health. Just show you one very one example. They try to demonstrate what's the advantage for AI-based approach. For example, that's one of the comments after we publish a paper about on schizophrenia. And then actually she's a professor in Harvard University. And so after we publish a paper on schizophrenia and on language side, and she jumped up, basically, she loaded comments about our results on schizophrenia. And what we try to see in our paper actually say, the language pathway is very important for schizophrenia. And she said that, was nothing new there, essentially, because she already worked on this, the historical pursuit of the language pathway for many, many years. So what's new for our approach, using AI approach, basically using data approach, data-driven approach? And our answer to her comments is that, yes, you're already working on this for many, many years on schizophrenia, but essentially it's a hypothesis-driven approach, So she specifies languages as a problem for language pathway, and she look into language pathway. But for us, might be different. We're using the data, and so what we try to do is we don't have any hypothesis there. It's data-driven approach, and we identify the language pathway is the most important pathway affected in schizophrenia. So we look at the whole brain, and we identify the language pathway is the most important pathway, and then we concentrate on the language pathway, from data-driven to target-driven. So that's the approach we use. So it's possibly different from the classic or historical research pathway, and I think that's a power of our data-driven approach. And I will show you a few examples later on, more concrete examples here. So when we look at all these, we look at many diseases actually, for depression, addiction, schizophrenia, dementia, Parkinson, OCD, for example. So so sometimes I use different diseases as an example, try to tell you what we are doing. So we look at this disease at a microscopic kind of genetic level and or cellular level, or more kind of brain image and the behavior level. And then we work out, for example, where's the origin, where's the root of disease, for example, depression, where's the root of the depression, and then we develop a methodology for prevention and for treatment. So I will explain to you, from the spatial scale, from micro scale to meso scale to macro scale, and then we develop the treatment or prevention side story, from very detailed level to the applications. For example, at the microscopic level, for the dementia cases, so we're using UK bank data, and essentially they have 50,000 people. They have around 2,000 protein available from all link. And what we work out is, so the question we ask for the dementia data or depression. We have work out a similar story for other diseases as well. For example, for dementia data, if you look at the protein here, and because we have this data available, and if you look at them, see, so that's the onset of your dementia, and it's very clearly you can see using the data, and you can see, say, 50 years ago around, that's a clear departure already. For example, for quite we selected 11 proteins here, for example, and so you can see, as that's a quite a clear picture there already using the data approach, and then we combine all these proteins. We select 11 proteins from. That's 2,000 protein. We select 10 of them around there, and then we use these 10 proteins and combine our machine learning approach, and we can predict, for example, 15 years ago, using all these protein panels and using our machine learning approach, and the AUC is around 0.91. So we can use the 10 protein, right, more exact, 11 protein, and combine our machine learning approach, and we can clearly predict the dementia 15 years ago, before the onset of the dementia. And
that's the young family.
Yeah, so as the paper was published a few 2 months back in Nature Aging, and highlighted in Nature, and that's the BBC News actually about, say, it's not about our paper, but I say,
If the NHS does prescribe the new drugs, they'll only be available to patients whose Alzheimer's is at an early stage. So speedy diagnosis will be crucial.
Yeah, so they involve the PBC program, they discuss about the importance of early diagnosis of the dementia, and in our paper, and it's highlighted in Nature actually. So that we told the story, we can, using all this machine learning and the data approach, we can early diagnose the dementia using our approach, basically using 10 proteins there. Yeah, so it's so it's at the microscopic level, at the protein, at the genetic level, using machine learning approach, I can tell you one example. Yes, just say for dementia, and we can work out a similar story for example, for depression as well, for Parkinson's, and also because of time, I don't have time go into details there, but then so that's one story for microscopic level, and I will tell you another story basically for macroscopic level. So I'll not go into detail at the cellular level there. So using for microscopic level, for example, at the excuse me, at the brain image level. And what we try to do is using all the data. For example, we're using sectional data. We collect a lot of data for depression people, and the question we ask there. So that's the data we have. We have one of the largest data for depression for brain imaging. So even a sectional data. So we collected around 4,000 people MRI data together. At one sectional data. And then the question we ask there is, can you use a machine learning approach to really say, first of all, subtype of all these depression patients? And secondly, can you predict the disease progression there as well? So it's not only the subtype of them, and also can you work out, how the disease progression? Yeah, so again, I don't have time go into details, but as a part, you can find our publication there and read the details yourself. That's the background idea how we can do it. So using sectional data, we can subtype depression into 3 subtypes. One is ACC, starting from ACC, gradually spread. Basically, the brain shrink. Yeah, so the shrink is spread to all of the brain. The second subtype is starting from the hippocampus shrink, gradually spread to all the brain. And the third one is frontal area, for in particular like OFC, shrink start from OFC and gradually spread to all of the brain. So we can basically, say find all these subtype and then also predict how the disease progression there. And then, for example, based on one of the findings, so we know the OFC shrink is one of the starting point for our depression disease. Then we can aim for this area, say target on this area, we can develop the treatment and the prevention of it. For example, for the treatment, we can use TMS, say target your natural OFC and try to inhibit the signal here, basically, and we can, and it's subsequently our colleagues they prove it works. For the area we found out for the depression, for example. And also we can use this for this approach, look at the prevention of depression. For example, we can work out if you have a healthy lifestyle, we can reduce the depression risk by 57% of the depression risk. So basically, I tell you is, using this data, we can look at the disease at the microscopic, mesoscopic, and macroscopic level, and then finally we can develop all this, into the prevention and the treatment as well. So that's a special side. So that's a geometry scale. We look at the different scale here. What we're missing here is, of course, the temporal scale. So. So we can even enlarge this geometric side. We look at the environment as well, how the environment affect the environment affect your depression, for example. Again, if you have interest, you can read our paper there. So from say geometric side, we can have all these scale available, look at them in a more kind of global comprehensive picture as well. But what we're missing here is, of course, that's a section of data in time in the temporal side. And so we can not only look at this spatial side, but we can also put all temporal side together. For example, we can have a longitudinal data, and then we can look at say what happens for example, for addiction, what happens for your brain. So we can have a picture in the spatial and the temporal scale as well. I say this will help us to explore the causality, for example, for addiction, why people start smoking, for example, and after smoking, after starting of smoking, then why you will become addicted to the smoking, for example, all this story. And so not only the spatial side, we can also look at the temporal side. How is the people, for example, substance as addiction people, for example, we can compare addiction with healthy people, and the discovery we have here is, for example, that's the healthy people, the brain size, and if you look at the addiction people for their lifespan, and that's the subcortex volume, gray matter of subcortex volume, and that's the gray matter volume of the cortex. And you can see, funny enough, for example, when they are younger, the addiction children, the subcortex brain is larger actually than the healthy people. And when they become older, and so the brain size for the subcortex actually is smaller than the healthy people. And the cortex is different picture here. So we need a kind of the panorama picture or comprehensive picture to understand the brain. It's not only the spatial side pattern changes, also the temporal side spatial changes as well. So that's my take-home message is here. So what we are doing for our AI side approach is we start collecting data. We have some of the largest data available, and then we use the AI algorithm. Then we try to have say discoveries. They try to identify the a starting point of the disease, for example, and then we can have the treatment and the prevention side of the story as well. And also, we can look at the spatial temporal. So that's not only spatial side, we can also look at a spatial temporal pattern. Then that's we very much believe. At the moment, so using all the AI approach, so we can identify the spatial temporal pattern change as well. And okay, I know my time is up, and then we can. So I tell you the story. So we look at the microscopic level and the macroscopic level and the treatment, and we try to unify them as well. So to unify, for example, as for schizophrenia, we unify the story, from the microscopic to the macroscopic. What happens, for example, the brain region shrink is linked to the neuron transmitter change here, for example, and the paper appear very soon in British Journal of Psychiatry. So we have this story, and I skip this part, man. Yeah, so I'm stop here. I try to convince the people maybe in the audience, using the AI and the data and combine with your knowledge, we can have some novel discovery and which will be useful for the treatment, for the prevention as well. Thanks.
Thank you very much, Jianfeng. Can you hear us?
Yeah, I can hear clearly. Yeah.
Which means that we have a couple of minutes for questions. If you have any questions, if you speak up, then Jianfeng will hear you out in Warwick. So any questions? Okay, so there's two. Okay.
Thank you for that speech. So I've got a question about you mentioned a lot of the complex predictive factors. What would that look like if it was implemented? Would that be a national screening process to look at those proteins? Would that be interval MRIs? How would that actually look like in clinical practice?
Very good question. Thanks a lot. Yeah, so that's published 2 months ago, I think, in Nature Aging, and you can find the paper there. Yes, we can do it, and we try to develop this protein panel, for the early prediction of the dementia there. And to me, we did look at the image side and the protein side. As to me, that is the most reliable at the moment. The biomarker we have figure out at the moment. But the trouble, I can tell you, in clinical applications, the trouble. Actually, I talked to all the people a few weeks back. For each protein, to identify, to have the data for each protein, we have to, the cost will be, say, a few £100 for each protein, around £200 possibly. So if we want to identify this 10 protein, have this protein panel, that will be quite expensive. And we talk to the All-Link, and what we want to do next is possibly we can reduce the price. If we can reduce the price, that will be really useful. I hope at least, for clinical applications. Yeah, thanks.
One more question?
That's one more. Thanks for your great talk again. As the size and diversity of your samples has increased, as the diversity in particular of your samples has increased, so comparing, for example, Chinese populations with Western populations, have you uncovered any surprising differences?
Again, very, very good question. We did look into the dementia, depression, schizophrenia, and we did compare, for example, this was not a depression, but schizophrenia. We compare using Enigma data, compare Chinese schizophrenia and Enigma schizophrenia. And funny enough, what we conclude is we are pretty much that, schizophrenia is one unified schizophrenia. There's no Chinese schizophrenia and American schizophrenia. We are pretty similar. So It's a very good question. For the cases we look at, depression at the moment. We look at depression and schizophrenia already. They are pretty much similar to each other. Dementia, we don't have enough data at the moment. For example, the protein data, but that's the thing we want to have a look at as well. Yeah, that's another very good question. I think. Yeah.
Thank you.
Good.